Hello, it's Keith here, and this is lesson 40 of the platform-specific series of my Z80 programming tutorials. Now we're going to be starting a new series relating to the CPC and some tricks that we can do with the CRTC that allow us to do graphics that are in some ways breaking the rules of the Amstrad CPC's graphics capability. We're going to be starting very simply this week with a trick known as EGX. Now, on the Amstrad CPC, if you're not familiar with it, there are two commonly used screen modes. Mode 0, which is 16 colour at 160 by 200, and Mode 1, which is 320 by 200 at 4 colour. Now, EGX combines the two and gives us basically a 320 by 200 screen, but allows us to have 16 colours on the screen as well. Now, this was first seen in the Imperial Mahjong game by Cargosoft, and I believe they actually invented the mode, and we're going to learn how we can do it today. Now, you can see an example screen here on my Amstrad CPC emulator. What I've done is I've converted the Chibi Akuma screen from the MSX, the 16 colour screen, into an EGX screen for the CPC. Now, we're going to have a look now at how this screen actually works, and we'll learn how the mode itself works. Now, the effect is actually a trick. What we're doing is we're alternating the screen mode every single line of the screen. So half the lines are mode 1 and half the lines are mode 0. So half the lines have a 320 pixel wide definition with 4 colours, and half the lines have 160 pixels wide at 16 colours. And this has the effect of giving us the smoothness of mode 1 and also the colours of mode 0. But of course we can't combine the two effects on the same line, so we do have to design our screen around this. Now you can see here is the EGX screen that you just saw. There's a screenshot of it, and each of these lines is made up of one of two combinations. So here are the mode 0 lines. You can see, for example, this skeleton here is green, and then here is the mode 1 lines, and you've got the smoothness of the text here, and especially the tops and the bottom, which is the chibiakumas.com logo here. And you can see here the skeleton is white. Now if you look at this one here, you'll notice that the skeleton is a combination of the two. You'll see some of the lines are white and some of them are green, and that's because the white is coming from here and the green is coming from here. And so we are trading off. We've neither got all of the colour of the 16 colour mode or all of the definition of the 4 colour mode 1 mode, but we are getting in some ways the benefits of the two, and that's how EGX works. So before we look at how to actually enable EGX on our CPC, we're going to discuss the actual technicalities of designing the screen. Now you can work in EGX on my Acusprite editor. If we just go to here and we select 4 colour, you'll see we can view a 4 colour screen. I'll just zoom out a little bit. So this is 4 colour mode, and we can go here and select 16 colour mode 0 here. And this would be the effectively 16 colour mode, but EGX alternates between the two every other line, and we have an option for that just here. If we select this EGX mode here, you'll see now the lines are being drawn accordingly. Now I did some of the touching up work in Acusprite editor, just to correcting pixels here and there, altering colours as required, but I only really designed Acusprite editor as a basic editor, so a lot of the work for today's example I actually did in Krita here. And what I've done is, if I just disable this layer here, so here is the mode 0 export. What I did is I took the 16 colour MSX screen, exported it in 16 colours, pasted it here, and then what I did is I pasted a mode 1 screen here, and then I put a layer on which is a transparency mask with interlaced lines, and you can see that is toggling between the two. I then copied this back into Acusprite editor here, and that's what I did to get the result. And then from here we can just export. But you'll notice here that I did have to make a lot of changes to make things as good as they could be. For example, the www.chibiakumas.com here is illegible. I made it twice as wide, and I touched it up using the mode 1 for the bottom and top lines to make them nice and defined, because these individual pixels here at the bottom of this W couldn't be done in mode 0, and that's something important to note. But when it comes to designing your EGX screen, you do have to make a lot of design choices to make it work as well as possible. So for example, the mode 1 part of the screen, I had to pick 4 colours that was going to work best with my screen. So I decided to use black, white, red and light blue, because I felt that these would give a good balance and also represented the most commonly used colours in the screen. And then when it came to the 16 colour part, I had to reposition some of the objects to make them as clear as possible. The text was moved to allow the tops and bottom lines to be in mode 1. That gave better detail, and you can see these are very blocky here in mode 0. I had to move these checkerboard kind of patterns here up a line to get them nice and neat in the EGX mode 1 here. which you can see these had to be moved up just very slightly, and a few other tweaks here and there were made just to try and make everything as neat as possible. So the important thing is, you know, with regards to the skull, for example, I had to move some of the pixels around. You're effectively trying to use the mode 1 to blend in the mode 0's smoothness, and using the mode 0 to add extra color to the mode 1 part. So it's not a true 320 by 200 screen, but it's very effective, and it does give a lot of extra color and a lot of extra detail when we use it. So that's the theory of the screen mode, but how do we actually make it work? Well, unfortunately, this is where the problem comes in. Now, there's no way that we can just call a system call or poke a certain address and that this is going to work for us. What we actually need to do is we need to start, when the screen starts redrawing, calculating each line as it's drawing and changing the mode ourselves. And this is the problem with EGX, and I think this is why Cargosoft chose to make a Mahjong game with very little graphical movement. You see, we're going to be using a large percentage of our processing power actually just repeatedly flipping the screen mode. And even worse than that is we're going to have to do it at very, very precise times. So we're going to have to make sure all of our other code is timed and fitted within the code that's going to be changing these screen modes. And we're going to be looking at that in just a moment. So when it comes to changing the screen mode, we're going to be using the gate array. We're going to be writing to port 7F, and then the other values are going to depend on the ROM and also the screen mode we want to change. And we're going to be toggling between mode 0 and mode 1, and the top of the screen is going to be mode 1. Now, on an Amstrad CPC screen, there are effectively 40 characters across the screen, but there's actually the border area as well. And when it comes to drawing a line off the screen, it actually takes the equivalent of 64 no operation commands to draw a full line. So if the system was drawing, for example, line 1 of the screen, and we had 64 consecutive no ops, then after those no ops completed, it would be in exactly the same position, one line below. And we are going to be using this to time things and to make our delays. Now, if we want to create 64 no ops, of course, we don't want to have 64 lines with NOP, NOP, NOP. What we can do is do DS64. No op on the Amstrad CPC is a byte 0, and so DS64 will create 64 zeros, effectively 64 no ops. If you don't have memory for that, of course, you could do a loop. I believe if you loop around 60 no ops with a DJNZ, I believe that's about right. But as I say, we're going to be using the DS64 in most cases here because it's nice and clear, and it just is a good way to start. Now, we're also going to be taking an advantage of a limitation of the Amstrad CPC. Now, when we change our screen mode, the CPC won't actually visibly change the mode until the end of the current line. So if we change mode from mode 0 to mode 1 and then back again to mode 0, and all of that happens within a single line, we won't notice any difference on the screen. Now, we could change to mode 1, wait 64 no ops or thereabouts, less the amount of commands needed to change to mode 1, then change to mode 0 and wait another 64 no ops. But if we time it so that the first mode change happens at the very end of a line, the second change will not actually be visibly occurring until the end of the next line. This means that we can have approximately 128 no ops and have a nice big gap to put some program code in before we need to do the next line mode change for the next pair of lines. Now, I know that sounds a little bit confusing, but don't worry about it at the moment because we're going to have a look at the code and hopefully it'll become a little bit clearer when we do that. So how are we actually going to run today's code? Well, we're going to be using WinApe, and I've got the source code loaded in. It's a file called CPC mode EGX here, and we need to actually load in the screen from BASIC. So what we're going to do is do an auto type here. I've got it prepared here. And so what we need to do is we need to load EGX test.scr, which is provided in my sources 7-zip. We need to load that into the screen memory at hexadecimal C000, and then we're going to run today's code at hexadecimal 8000. So I just need to compile today's code, and it's run with no errors. And let's just run it now. So you can see the screen's loading into memory there, and then it flicks, the colors change because my code today changes the colors, and then you can see we've got the EGX effect here, and we can see we've got approximately a 320 by 200 screen in 16 colors. There we go. So let's have a look at the code that does the dirty work for us today. So we've got some stuff here that's very common to our tutorials, some palette code here. We've covered palettes in the past, so if you don't know about palettes, please have a look at one of my other tutorials. But the code we're going to be looking at is really starting here. Now, the first thing we're going to do is we're going to disable the interrupt handler. We need total precision, because if we're even one or two ticks out, then we're going to be completely all over the place and the code won't work. And I'll show you in a moment what happens if things are out. So the first thing we're doing is we're putting an enable interrupt and a return at hexadecimal 0038 here, and that is the address of the interrupt handler. So we're effectively making it an empty interrupt handler. We need interrupts to occur for our timing, but we don't want them to do anything. So we're checking that interrupt mode 1 is set, and we're enabling interrupts here. Next, what we're doing is we're reading in from the PPI chip, and we're waiting to see when a VSync occurs. VSync occurs at the top of a screen, so we're effectively waiting for a full screen redraw. So we do that by checking bit 0, and when bit 0 is 0, we're just looping around here. When it becomes 1, then we know we're at the top of a screen. What we're doing next is we're doing a halt. Now, this is because I was having some problems with one time in about 10, it wasn't working properly, and I think what was going wrong is that if a VSync is occurring as your program runs, then you will get a VSync when you first run this, but you might be kind of halfway through that VSync, just a few ticks in, and this is so precise, it has to be absolutely exact. So what I'm doing is I'm waiting for VSync, and then waiting for another interrupt, and so we'll now be 1/6 of the way down the screen, and at this point we know we're not in the first VSync. We know we're at a very, very precise time because we've waited for that interrupt, and now we can really start to work with very precise timing here. So now we're in the main loop, and this will run for every single frame that the Amstrad CPC draws, because remember, it's the Z80 doing the work of the constant mode switching. So even though it looks like a still screen, there's a lot of processing work being done to keep that still screen being drawn. First, what we're doing is we're loading in again in the exact same way as we did here, reading in from the PPI at F5XX. Any address in F5 from F500 to F5FF will work for this. We're reading in and we're waiting for that VSync here. Now, when we get a VSync, we're now at the top of the screen. We need to now wait until the first drawing line to start this mode flipping effect. So what we're doing here is we're waiting. Remember, there's 64 no-ops per line, and we're waiting for 32 lines, which is approximately the time the actual VBlank takes to occur. So this is the time that is actually outside of the screen area altogether. Once we've done that, we now need to wait another 32 lines, and this is effectively the border before the actual first drawn line of a standard CPC screen. When we get to this point, we're actually ready to start drawing the lines of the screen. So what we're going to do is we're going to do 100 pairs, a 200 line screen, 2 screen mode changes per pair of lines, so 100 pairs of lines here. Then we're waiting another 32 ticks, and this is the amount of time that it takes for us to get to the far right of the screen, because we need to make both mode changes. The first will happen at the end of a line, the second will happen just after the start of the line, and that will mean the second mode change won't really occur until the line afterwards, because as I said, the screen mode can only change once per line. Now this is that code that's going to loop around until IYL reaches 0. Now you'll notice here there's all of these numbers here. These are the number of ticks that each command takes. Now each command within the Z80 takes a certain amount of time, and we're having to compare them all to a no-op command. Now a no-op command takes 4, and a command like this will take 12. So we need to be very careful that we know how many ticks each command will take, and that's what we're doing here. And unfortunately, the Z80 documentation, which I've provided in the past, while correct according to the Z80 specification, doesn't actually represent the correct amount of ticks that the commands will take on the Z80 when it's running on a CPC. I'd suggest you have a look at the CPC Live website. There's a link on my website, and I'll put it in the comments of this video, because as I say, that's got far better information than I can provide at the moment. I'm trying to get the information copied over to my Z80 cheat sheet, but it's going to take some time. But anyway, what I generally suggest if you're just starting out with this kind of thing is start very simply and just try tweaking your code, and hopefully you'll be able to see when it's right, and just keep adding and removing no-ops and delays just until the effects become stable, because you will notice very quickly if they're not stable. So anyway, so at this point we're now in the loop for doing our line, and what we've got here is we've got a call for the screen mode. Now the syntax of this you can see just here. The top bit needs to be 1, then 0. We need to set the high and low ROM options, and we've got our 2 mode bits here. Now we're turning off the ROM with these 2 bits. We're selecting that option with the top bit set to 1, and here we're selecting mode 0. We're then incrementing C to set to mode 1, and we're decrementing it again here. So we're changing to mode 0 and we're changing to mode 1. Now you can see again we've got all the ticks calculated here, and then we've got a delay here of 110, and this is 120 no-ops. And if we were writing a game, this is where you'd need to put your game logic, your playing of the sound, reading of the joystick, but you'd need to make sure whatever you did here took the equivalent of 110 no-ops, because if it takes less than that and you don't have any padding, then the effect isn't going to work, and if it takes more than that, then the effect isn't going to work. And this is why EGX is so difficult to use, and a lot of these raster effects, these CRTC tricks, are so difficult to code because you're having to actually code around this very, very precise timing option. And I'll show you later what will happen if I just make a one tick mistake, because it's going to go AWOL. So we'll see that in just a moment. And then we're decreasing IYL here, and we're looping back up to here. And this is really all that's doing the work. The code is very simple. Change the mode, and wait. And it's actually calculating the weights, the tricky thing, because it's making this effect stable that's the hard thing. So what I'm going to do now is I'm actually going to change this code. So let's compile it as it is for now. So we've just loaded that into memory here. And then if we just load this up to here, and we just load this onto the left-hand side here. So there's our EGX effect working just fine. So what happens if I change this to 109 here? Well, you can see things have gone quite horribly wrong. So you've got the mode changing correctly on the top line here, and there's something going on in the middle, but it's not good. And all that was one no-op missing. Now if I put it back, the effect's fine again. So that was within the main loop. So if we were doing some joystick reading and it took a little bit too little time, that's what's going to happen. And if I change this by increasing it to 1, exactly the same thing. That's how precise we're having to be with this code here. And now I've just caused a crash. That's because I was recompiling the code into memory while the code was running. So it's probably jumped to an illogical place here. So if I just reset that, and that's why I used my auto type function here. So we can just load this again. Oops, I forgot to compile my code there. So just do that again. So there, our effect is back again. So now what happens if I change this first delay? This is the first delay before the screen starts drawing, and I change this to 31 here. Well, now we've got it flicking on and off. And again, we've got what the problem we've got here is that we're sort of at the end of the line, but not quite. And so just depending on when the timings are occurring, maybe our effect is working fine, maybe it's not working at all. And again, if I change this to 33, again, more problems, 34, flickering very fast here. So what was it? 32. There we go. So as I say, we have to be precise with that timing as well. Another thing we can do, if we change this to 50, now only half of our screen has the EGX effect, but we'll have a lot more processing power free, of course, because at the bottom of this, all of the processing power is free again. And so one thing you could do is, depending on how much of your screen is covered by EGX, you will have some processing power left. If you were using a very small screen, you would have a lot more power. And again, this is why Cargosoft's Imperial Mahjong was so damn clever, because I believe that was overscan. So they were using the entire visible area of the screen, and really they were having to code around these tiny little 100 no-op slices of processing power that they could work in. And that's really where the incredible skill of the people who write these kind of games comes in. It's not designing the EGX graphics, it's not really making the sound or designing the logic to the game, which, don't get me wrong, are very impressive feats on their own. It's working out how you can do this within precision timing, slice it all up, and then somehow, you know, keep everything stable when, as you see in these examples, just the slightest mistake and your screen will go crazy. And if you think it's a bit crazy this week, wait until you see next time when we're going to be looking at the rupture effects that you can use to do a very, very clever effects in games. So as I say, I mean, people are in awe at the moment at this Vespertino game, and it is incredible, but it's not just the incredible graphics that are being displayed, it's the incredible precision and dedication to debugging that is being shown by the authors of those games, because if you make a mistake, your screen is not going to show anything you can even see. It's absolutely crazy. So as I say, that's I'm just trying to iterate here just how precise you have to be in your programming. But if you were using an overscan screen, you could change this to 150 or something, whatever you needed. And another thing is, let's say if we change this to just 16, we're now starting the EGX effect early, and the effect has been that the bottom of the screen now isn't being drawn properly. You might need to do this again. If the start of your screen was higher up, you would want to start the effect earlier. But in this case, we would just be wasting processing power doing that. Now, if you were looking to use this in a game kind of crudely, what you could do is you put this in your interrupt handler and maybe start at the first interrupt, which would happen about 2 lines down into the screen, and so maybe you could have those top 2 lines blank, and then you could just have the EGX effect for the visible screen, and then when the bottom of the screen's been drawn, you could return from the interrupt handler, and that would give you a little bit of processing power to play with without having to do this thing of slicing your program up into 110 no-op chunks. But as I say, you're not going to have much processing power left, so you'd be only doing very basic games with that. I did see someone comment that they'd like to see an action game in EGX, and of course we all would, but I think it's going to be really impossible because of the amount of processing power which is being used to maintain this effect, and also the complexity of programming sprite routines and things. With Chibi Akuma's, I was really optimizing the code for speed all the time. Well, in this case, you've got to optimize your code for consistency with regards to how many no-ops it takes. You've got to be able to switch back your screen mode every 110 no-ops or thereabout. So that's got to be a priority when you're developing if you're going to be using this screen mode. So there we go. So that's a brief introduction to EGX, and also a brief introduction to how we can manipulate the CRTC's graphical abilities to make it do things that it really wasn't designed to do. This is the first of 3 episodes. The next 2, we're going to look at something that's known as rupture. This is where we can do split screen and hardware scrolling and all kinds of really crazy hardware tricks. Next time we're going to look at how we can do split screen, and I'm going to give you some more practical code that you don't need to do all of this nasty stuff of working around these no-ops and very precise timing. I've got a very simple scrolling routine that allows for some hardware split screen and split screen modes that will work with a standard interrupt handler, so you can just write your game and as long as interrupts are enabled, it's going to work fine. Then we're going to look at an even more complex example, and we're going to look at how you can use the CRTC effects to actually completely synthesize a screen that barely exists in memory at all. So you're going to see a full overscan screen that's made up of just 8 lines of memory within the system, and we're going to learn how we can do that. And I think this is going to be a bit interesting to people who are curious about how these games like Vespertino are now doing these incredible graphics that we've never seen before on the CPC, and don't understand how the CPC is honestly capable of something so fast and impressive with so little memory and so little processing power, relatively speaking. Anyway, I hope you've enjoyed this lesson. Thanks for watching, and goodbye.